So before we go on to look at the proxies we use to infer the past climates, we have mentioned several things about the climate during past events of migration, evolution, behavioral changes, East African reedification, and so on. The proxies give us a good idea of climate in the past, but sometimes to fill in the gaps left by the data, which are very sparse, we use models for construction of past climates, for present weather and climate predictions, and of course for future climate projections. So we'll just run through one podcast on the conceptual framework of the climate system, and the concept of Earth system emerges right out of that. Typically, climate system looks mostly at energy, ocean, atmosphere, land, weather, climate. When we say Earth system, typically we add carbon cycle, sometimes more details like humans, vegetation, marine ecosystems, and so on. And I feel the wind here, so let me see how bad is the sound. So let me just go through this. I have, as I said, a whole course on introduction to climate modeling, and there is one set of podcasts which is called Demystifying Climate Models, which explains these models without any equation. So maybe that will help you as well. So here we go. Climate forcing agents that we already looked at, greenhouse gases, non-CO2 greenhouse gases in addition to CO2. So methane, ozone, halocarbons, N2O. Aerosols affect climate, of course. Land use, so deforestation, urbanization, agriculture, etc. that we talked about, volcanic eruptions, and solar irradiance changes. They work at multiple time scales. The instantaneous radiative forcing is the fast time scale, resulting in effective radiative forcing, so the change in balance at the top of the atmosphere, which is not obviously instantaneous because it has to go through the system. That results in radiative balance, which includes how much heat is going into the ocean, and that leads to temperature change, which then leads to climate impacts, not only anthropogenic change and global warming, but even the seasonal changes or heat waves and so on, which could very well be natural. And then it feeds into the range of feedback processes that we talked about. The wind is strong, sorry, let me see. Planck feedback, so the frequency of outgoing long wave radiations and incoming radiation that is absorbed by greenhouse gases at various frequencies and so on. Clouds, lapse rate is the rate at which the temperature changes from the surface to the top. That determines energy balance and circulation, and is a result of circulation as well. Water vapor, of course, if temperatures cool, atmosphere cannot hold as much water vapor as it is warm, but if it warms and water vapor increases, then you have water vapor as a strong greenhouse gas which traps more radiation and makes it warmer further. Land surface albedo, atmospheric chemistry, and so on. And we have also ocean circulation, ocean chemistry and biochemistry, and weathering, which is the carbon cycle feedback. Temperature and changes and precipitation changes also affect the weathering rates, for example. In general, it's a geologic timescale process, so we are mixing all the time scales here. Dynamic vegetation and terrestrial ecosystems, so C3, C4 we mentioned briefly. So there's a long time scale vegetation response, but there is also a seasonal vegetation response and potentially vegetation response to human activities. Permafrost carbon that we mentioned, snow and ice cover, and so on. Again, altogether coming back to change other climate variables and climate impacts. On longer time scale, we have terrestrial carbon uptake, carbon cycle that we are not going to get into details, and ocean carbon uptake, which can put away ocean greenhouse gases and CO2 and so on for a longer time, as we saw with the heat. So ocean can take up heat as well as greenhouse gases, right? So Obviously, it's a very simplified conceptual framework. Actual model itself will be very complicated because it has nonlinear equations in conserving momentum, energy, mass, and thermodynamic equations in terms of the change of state from water to water vapor to clouds and rain, and in the ocean you have salt, so you have deep water forming, light water forming, and so on and so forth. And these equations cannot be solved by paper and pencil analytically, so we discretize them and put them onto a grid in a computer. So this is how it would look like. We would take the sphere and create a number of grids in the atmosphere, in the ocean, on the land, and each grid then exchanges material and gases, so CO2, dust, H2O, water vapor, temperature, advections, winds, moving things around, and so on. So the concept of climate modeling here would then be balancing energy emitted and reflected radiation, energy coming in, incoming solar radiation, momentum and energy being advected around, ocean being dragged by the winds, ocean taking up the heat, ocean evaporating and providing water vapor to the atmosphere, which is a major way of energy being moved around. So in a simple sense, I'm sure you've learned that because Earth is a sphere, per unit area more energy is coming in at lower latitudes than at higher latitudes, so there is an equator to pole temperature gradient, but the poles and incoming radiation is balanced by outgoing long wave radiation. There is excess energy resulting in the low latitudes and deficit energy at high latitudes, so energy has to be constantly moved from excess energy regions to low deficit energy regions, because poles don't get colder and colder. They are cold but they remain so, and low latitudes don't get warmer and warmer, which means energy is being moved around. The result is, of course, the winds and clouds and rainfall and momentum and energy transport and so on and so forth. So lots of details. In a simple sense also, how many grids we put in determines how finely we are representing the processes, but as you increase the number of grids, the amount of computing power needed goes up, plus integrating it becomes slower and slower. So if you want to integrate 135,000 years of climate, for example, you cannot do it with a very high resolution model. But on the other hand, when you want to forecast weather, you want to be able to say at a very high resolution how temperatures will change, how precipitation distribution will happen, and so on. And there are details. In general, models have easier time simulating let's say temperature compared to precipitation, because we don't fully understand the processes which form clouds and rain and so on and so forth. Okay, given that in the long run, for the past and for the future, we want to take forcing generated by human beings. So here we look at the carbon in terms of gigatons since the Industrial Revolution, let's say. So how has fossil fuel burning led to increases in carbon? How have land use changes led to source of carbon to the system, and where that carbon is going in terms of the ocean, the land, and what accumulates in the atmosphere. Obviously, reconstructing the budget is not easy, so sometimes you end up with residuals. So total estimated sources do not meet total estimated sinks in some cases, which are called imbalance or missing sink, and so on and so forth, because we still don't know the impact of things like carbon fertilization that we talked about, enhanced carbon uptake by vegetation, which may be putting away carbon into some places, wetlands, maybe peatlands, and so on and so forth. But you can see that as the atmospheric CO2 has increased, the amount going into the ocean and land sink have increased as well. And of course, atmosphere is seeing more and more CO2 from the Charles Keeling curve. We know that CO2 was at about 280 ppm at the beginning of the Industrial Revolution, and now we are at about 420, the highest in a very long time. So that's kind of what models also have to include and simulate for projecting into the future. So projections of the future are typically few decades to a century, and they have increased in complexity and resolution and so on to make them more realistic. In general, you look at the grid cells here in a log scale for the atmosphere and the ocean, and you have number of interacting components. Can be just a box model which does only the atmosphere, only the land, or only the ocean, or you may have many other components: ocean, atmosphere, land, carbon, vegetation, and so on and so forth. And there is a cumulative dimension being represented of the atmosphere and the ocean, and that corresponds to the feedback as well. So there is a spectrum of models on this in this phase space. So Burn 2.5D is one model that's been used quite extensively, is a simplified model, as you can see. But if you go to full general circulation models, atmosphere, ocean, land models, you end up here with high number of grid cells, large number of cumulative dimensions, and these simulations require a lot of computing power and so on. So there are many models in the middle. EC built Clio, Goldstein Puma, Genie, Climber 2, and so on and so forth. So UVic model that we already mentioned, and some results we will look at, come from somewhere in the middle here as well. It's a simplified model that runs can be run for a long time with not much computing power. So that's the point. You're trying to optimize number of processes you want to represent and the complexity. If your main goal is to look at how atmosphere and ocean have changed at a coarse resolution over 135,000 years, you wouldn't run a full GCM, which will be very expensive. You will use something like a UVic model somewhere in the middle in terms of the complication in grid cells, cumulative dimensions, and number of interacting components. Okay, so we'll come back and look at the proxies and some results from simulation of a UVic model for the last 135,000 years before we go on to look at the details of the so-called marine isotope stages, which are these millennial timescale cooling and warming periods within the glaciation that happened beginning at about 135,000 years to about 21,000 years, when the glaciation reached its maximum, and then deglaciation started, and it was completed to the current stage at about 10,000 years ago, and Holocene happened, during which we have basically evolved into modern human beings, agricultural and now industrial technological human beings. So that's the kind of sequence we want to look at with paleoproxies and models to try to understand climate impact on our evolution over this critical period of 135,000 years. Okay, so I'm going to leave this here and make sure that the sound is okay in terms of the wind rustling through the microphone. Okay.